So sometimes when we're evaluating limits, we can get stuck and we end up with something called an indeterminate form. In this video, we're going to talk about the indeterminate form of 0 divided by 0. And when that occurs, there's a little trick we can use. Or not trick, it's a rule, and it's called L'Hopital's rule. So this occurs when we're evaluating the limit and we end up with 0 over 0. So let's take a look at if we were evaluating this limit as x approaches 0 of 1 minus cosine x over x. Well, that would be a 1 minus cosine of 0 divided by 0, which is a 1 minus 1 over 0, and so we end up with 0 over 0, and we can't do that. And it's undefined is technically where we end up, but we can evaluate that limit. Now, previously what we would have done is graph this and use that graph to evaluate. What we want to do here is evaluate graphs. We want to evaluate this algebraically. So, L'Hopital's rule, it says if we are evaluating some limit as x approaches a of f of x divided by g of x, and we end up with 0 divided by 0, then what we can do is evaluate, or rather, if we're evaluating that limit as x approaches a of f of x divided by g of x, what we can do is evaluate the limit as x approaches a of the derivative of f of x divided by the derivative of g of x. So we're taking the derivative of the numerator and denominator separately. There are YouTube videos in the OpenStax book too. They talk about the proof of this. We're just going to go ahead and jump in and use it, but if you're interested in the proof, it is out there. But we're going to go ahead and just start applying this. So we tried to evaluate the limit and we ended up with 0 over 0, which is an indeterminate form. So I know I want to use L'Hopital's rule. So I'm going to evaluate the limit as x approaches 0 of 1 minus cosine x divided by x. And what we're going to do is say this is equal, and because of L'Hopital's rule, I can write this as the limit as x approaches 0, take the derivative of the numerator, so I'm completely ignoring the denominator right now. A common mistake here is applying the quotient rule, but we're not applying it to the whole thing, it's just the numerator and denominator separately. So I'm keeping them separated. Derivative of 1 minus cosine of x would be a negative sine x, so a positive sine x, divided by the derivative of just x, which is a 1. So what I'm really doing here is evaluating the limit as x approaches 0 of sine of x, which is the same as evaluating sine of 0, which sine of 0 is just 0. So let's check this visually. And the goal is to avoid graphing it, but just to get a little proof that this is working for us, I'm going to graph the function 1 minus cosine of x over x. And here we are, and we're evaluating as x approaches 0. Now at 0 itself, it's undefined. What we can see is as we approach from the left and approach from the right, we are in fact approaching an output of 0. So our limit works there, and we could actually evaluate it algebraically after applying L'Hopital's rule. Let's check out this next one. So let's say we're trying to evaluate the limit, so this would be sine of pi over natural log of 1. Sine of pi is equal to 0, divided by natural log of 1 is also 0. So seeing that 0 divided by 0, I know I want to use L'Hopital's rule because that's an indeterminate form. So evaluating this limit as x approaches 1 of sine of pi x over natural log of x, what we can do is apply L'Hopital's rule to be evaluating the limit as x approaches 1, so that piece doesn't change. I'm keeping my fraction. Derivative of sine is cosine, So we're going to have cosine of pi times x. And then with our chain rule, we'll also be multiplying by a value of pi divided by natural log of 1. Nope. Derivative of natural log, which is 1 over x. And now we're going to plug in x equals 1. So plugging in x equals 1, we'll have pi times cosine of pi over 1 over 1, which is pi times cosine of pi is going to be a negative 1. So this is all ending up at negative pi for a final answer. And we could check that out by graphing our original function, and as x is approaching 1, we should see an output around negative pi, even though it's undefined for our function. All right, next up, let's see what happens if we kind of plug in the idea of infinity in here. So in the numerator, that's like having e to the power of 0 minus 1 over 1 minus 1 divided by infinity is like essentially 0. So there's our indeterminate form of 0 over 0. And what we're going to have here, so this limit as x approaches infinity of e to the 1 over x minus 1 over 1 over x. And actually, I'm going to rewrite this as x to the negative 1 and x to the negative 1 down here, just for the sake of taking derivatives. So applying L'Hopital's rule, we're still taking the limit as x approaches infinity. Now I'm going to take the derivative of the numerator. So e stays the same, but then it needs to multiply by the derivative of x to the negative 1. So that will be a negative x to the negative 2. And then derivative of minus 1 is just 0 over derivative of x to the negative 1. So we'll have negative x to the negative 2. We end up with a really nice cancellation there. So really we're just evaluating the limit as x approaches infinity of e to the 1 over x. And if we think about plugging in infinity, that's like having an exponent of 0, which all simplifies to 1. All right, one more case here, and then we'll go on to another indeterminate form. But if we plug in 0 here, so that's like having sine of 0 minus 0 over 0 squared. That's big 0 over 0. So that tells me I want to try to use L'Hopital's rule. So taking our limit as x approaches 0 of sine x minus x over x squared, applying L'Hopital's rule, we're taking the limit as x approaches 0. Derivative of sine is cosine. Derivative of minus x will be a minus 1. All over derivative of x squared is 2x. And if I go to plug in 0 here, I would have cosine of 0 minus 1 over 2 times 0, which is a 1 minus 1 over 2 times 0 is 0. So we end up at our indeterminate form again. So what I want to do is, instead of ending up there, I'm going to apply L'Hopital's rule again. So if you keep getting the indeterminate form, you can apply this L'Hopital's rule until it works, basically. So I'm still evaluating the limit as x approaches 0. So derivative of cosine x is negative sine x. Derivative of minus 1 is 0, all over 2. And now we should be all good to go with a negative sine of 0 over 2, which is a 0 over 2, which will just be 0. So we can apply it more than once until it works out if you keep getting that indeterminate form.